My dear students, in this video, we will understand breadth first search and depth first search. See, for traversing a binary tree, we have three tree traversal methods. They are pre-order traversal, in-order traversal, and post-order traversal. For traversing a graph, we have two important graph traversal methods. They are breadth first search, that is BFS, and depth first search, that is DFS. We'll understand the basic concept of BFS and DFS and also the difference between both of these. Now, to make you understand the concept of breadth first search and depth first search, I have taken a simple example. I have considered a course. In that course, there are three chapters: Chapter 1, Chapter 2 and Chapter 3. In Chapter 1, there are four sections: Section 1, Section 2, Section 3, Section 4. Similarly, in Chapter 2, there are four sections, and Chapter 3 also there are four sections. Yes, Chapter 1, four sections, Chapter 2, four sections, and Chapter 3, four sections. First, let us understand how actually these sections will be traversed using BFS. That is breadth first search. Yes, breadth first search. See, in breadth first search, the sections are traversed breadth-wise. That is, Section 1 of Chapter 1. After that, Section 1 of Chapter 2. After that, Section 1 of Chapter 3. Yes, breadth-wise they are traversed. Section 1 of Chapter 1, Section 1 of Chapter 2, Section 1 of Chapter 3. Then, Section 2 of Chapter 1, Section 2 of Chapter 2, Section 2 of Chapter 3. Yes, breadth-wise. Yes, Section 2, Section 2, Section 2, yes. Next, Section 3 of Chapter 1, Section 3 of Chapter 2, then Section 3 of Chapter 3. Yes. After that, last, Section 4 of Chapter 1, Section 4 of Chapter 2 and Section 4 of Chapter 3. Yes, breadth-wise. So this is how we are going to traverse using breadth first search. Breadth-wise we are traversing. Now let us see how actually we traverse using depth first search. In depth first search, first we start with Section 1 of Chapter 1. Then immediately we go to Section 2 of Chapter 1. Next, Section 3 of Chapter 1. Next, Section 4 of Chapter 1. So we go depth-wise. We finish the complete Chapter 1, all the four sections of Chapter 1. Then we go to first section of Chapter 2. We finish all the sections of Chapter 2. Then we go to Chapter 3. We finish all the sections of Chapter 3. That is Section 1, Section 2, Section 3 and Section 4 of Chapter 1. Then again the four sections of Chapter 2. Yes, depth-wise. Then the four sections of Chapter 3. Yes, this is how we traverse in depth first search. In breadth first search, a graph is traversed breadth-wise, whereas in depth first search, a graph is traversed depth-wise. I think this simple example will give you the conceptual difference between breadth first search and depth first search. Now, let us understand the differences between depth first search and breadth first search. BFS stands for breadth first search, whereas DFS stands for depth first search. Number one. Number two, BFS traverses the graph breadth-wise, whereas DFS traverses the graph depth-wise. Number two. Number three, BFS traversal is done with the help of queue data structure, whereas for DFS we use stack data structure. This is an important difference. BFS uses queue, whereas DFS uses stack. We will understand how actually the queue and stack are used when we come to the algorithms operations of BFS and DFS. BFS is more suitable for searching vertices which are closer to the given source. In BFS, we are going to traverse breadth-wise. Therefore, it is faster to search the vertices which are closer to the source. Whereas DFS is more suitable for searching vertices which are far away from the given source, because DFS will traverse depth-wise. Therefore, it is faster to search the vertices which are far away from the source. BFS can be used to check the connectivity and acyclicity of a given graph, and the same thing is true for DFS also. The time complexity when the graph is represented by adjacency matrix is big O of V squared in case of BFS. In case of DFS also, it is the same. So, when the graph is represented by adjacency matrix, in both BFS and DFS, the time complexity is big O of V squared. The time complexity when the graph is represented by adjacency list is big O of number of vertices plus number of edges. In case of BFS and in case of DFS also, it is same. So, these are the 7 comparison points for BFS and DFS. Now let us see the operation of breadth first search. For that I have considered a graph. Bengaluru, Chennai, Hyderabad, Thiruvananthapuram, Mumbai, Bhubaneswar, Bhopal, Raipur, Gandhinagar, Kolkata, Patna, Jaipur, New Delhi. So this is our graph. Let us see how we traverse this graph using breadth first search. And also we will consider source vertex as Bengaluru. Initially, we will consider the visit value for all the vertices is equal to 0. So visit for all the vertices is equal to 0 because none of the vertices are visited. Okay, therefore all the vertices visit value is 0 initially. Now we will consider a queue. This is our queue. Yes, and this is our BFS traversal. Now the source vertex is Bengaluru. Therefore, Bengaluru is inserted into the queue. And whenever you insert a vertex into the queue, make the visit value equal to 1. Therefore, visit of Bangalore becomes 1. Now, let us start our operation. Is the queue empty? No, the queue is not empty. Therefore, remove the front element of the queue. Front element is Bangalore. Therefore, we remove the front element and we add it to BFS. So, Bangalore is added to BFS. After adding Bangalore to BFS, you find out what are the vertices adjacent to Bangalore. There are 4 vertices adjacent to Bangalore: Chennai, Hyderabad, Thiruvananthapuram and Mumbai. Because we have direct arrows from Bangalore to Chennai, Bangalore to Hyderabad, Bangalore to Thiruvananthapuram and Bangalore to Mumbai. Now, we will add all the vertices adjacent to Bangalore to the queue. First we will add Chennai and make visit of Chennai equal to 1. Then we will add Hyderabad, make visit of Hyderabad equal to 1. Then we will add Thiruvananthapuram at the end of the queue and make visit of Thiruvananthapuram equal to 1. Then we will add Mumbai to the end of the queue and make visit of Mumbai equal to 1. Yes, all the 4 vertices of Bangalore are added at the end of the queue. Very good. Now again come back. Is the queue empty? No, the queue is not empty. Remove the front element of the queue. What is the front element of the queue? Chennai. Therefore, remove Chennai, add it to BFS. Find out what are the vertices that are adjacent to Chennai. Chennai has got only one vertex which is adjacent, that is Bhubaneswar. Can we add Bhubaneswar to the end of the queue? Check the visit value. Visit of Bhubaneswar is equal to 0. It means Bhubaneswar is not yet visited, therefore Bhubaneswar can be added to the end of the queue. Yes. Add Bhubaneswar to the end of the queue, and whenever Bhubaneswar is added to the end of the queue, make visit of Bhubaneswar is equal to 1. Very good. Chennai is over. Again, come back. Is the queue empty? No, the queue is not empty. Therefore, remove the front element of the queue. What is the front element of the queue? Hyderabad. Remove Hyderabad, add it to BFS. Now, all the vertices that are adjacent to Hyderabad, we should check. There are 2 vertices that are adjacent to Hyderabad, that is Bhopal and Raipur. Can we add Bhopal? Check visit of Bhopal whether it is equal to 0. Yes, visit of Bhopal is equal to 0. It means Bhopal is not yet visited. Therefore, Bhopal can be added at the end of the queue. And when you add a vertex at the end of the queue, immediately make visit of that particular vertex is equal to 1. Therefore, visit of Bhopal becomes 1. Next, Raipur. Can we add Raipur to the end of the queue? Yes, because visit of Raipur is equal to 0. It means it is not yet visited. Therefore, Raipur is also added at the end of the queue and immediately you make visit of Raipur is equal to 1. That's all. All the adjacent nodes of Hyderabad are taken care of. Therefore, again come back to the queue. Is the queue empty? No. Remove the front element of the queue. What is the front element of the queue? Thiruvananthapuram. Add it to BFS. Now find out what are the nodes adjacent to Thiruvananthapuram. There is one node which is adjacent to Thiruvananthapuram, that is Mumbai. Can we add Mumbai at the end of the queue? No, because visit of Mumbai is already 1. meaning Mumbai is already visited, therefore Mumbai cannot be added at the end of the queue. Very good. We cannot do anything because Mumbai is already added. Nah? Okay. Again come back. Is the queue empty? No, the queue is not empty. Remove the front element of the queue. Therefore remove Mumbai. Add it to BFS. Find out what are the nodes adjacent to Mumbai. There are two nodes adjacent to Mumbai, that is Raipur and Gandhinagar. Can we add Raipur? No, because visit of Raipur is already 1. Therefore, Raipur cannot be added to the end of the queue. Okay. Next, consider Gandhinagar. Can we add Gandhinagar to the end of the queue? Yes, because visit of Gandhinagar is equal to 0. Therefore, Gandhinagar can be added at the end of the queue. And after adding to the end of the queue, immediately visit of Gandhinagar will become equal to 1. That's all for Mumbai. Now again come back to the queue. Is the queue empty? No, the queue is not empty. Therefore remove the front element of the queue. What is the front element of the queue? Bhubaneswar. Remove Bhubaneswar, add it to BFS. Find out what are the nodes adjacent to Bhubaneswar. Adjacent to Bhubaneswar you have Kolkata. Can we add Kolkata to the end of the queue? Check visit of Kolkata. Yes, visit of Kolkata is equal to 0. It means Kolkata is not yet visited. Therefore, Kolkata can be added at the end of the queue. Yes, Kolkata is added at the end of the queue. After adding Kolkata at the end of the queue, make visit of Kolkata equal to 1. Bhubaneswar is over. Again, come back to the queue. Is the queue empty? No. Remove the front element of the queue. What is the front element of the queue? Bhopal. Yes, remove Bhopal, add it to BFS. Find out the adjacency nodes that are adjacent to Bhopal. Adjacent to Bhopal, you have Patna. Can we add Patna to the end of the queue? Check visit of Patna. Visit of Patna is 0. Yes, we can add because Patna is not yet visited. Therefore, Patna can be added at the end of the queue and visit of Patna becomes 1. That's all for Bhopal. Again, come back. Is the queue empty? No, the queue is not empty. Remove the front element of the queue. What is the front element of the queue? Raipur. Remove Raipur, add it to BFS. Again, find out the nodes that are adjacent to Raipur. Adjacent to Raipur, we have only Patna. Can we add Patna to the end of the queue? No, because visit of Patna is already 1, meaning Patna is already visited. We cannot add Patna again. That's all for Raipur. We cannot do anything. Come back to the queue. Is the queue empty? No, the queue is not empty. Remove the front element of the queue. Yes, the front element of the queue is Gandhinagar. Remove Gandhinagar, add it to BFS. Now, what are the nodes adjacent to Gandhinagar? There is only one node adjacent to Gandhinagar, that is Jaipur. Can we add Jaipur at the end of the queue? Check visit of Jaipur. Visit of Jaipur is equal to 0. Yes, since visit of Jaipur is equal to 0, Jaipur is not yet visited. Therefore, Jaipur can be added at the end of the queue. And whenever Jaipur is added at the end of the queue, immediately visit of Jaipur becomes equal to 1. That's all for Gandhinagar. Again, come back. Is the queue empty? No, the queue is not empty. Remove the front element of the queue. What is the front element of the queue? Kolkata. Kolkata is removed. Added to BFS. Now find out what are the vertices that are adjacent to Kolkata. There is one vertex that is adjacent to Kolkata, that is New Delhi. Can we add New Delhi to the end of the queue? Check visit of New Delhi. Yes, visit of New Delhi is equal to 0. Therefore, New Delhi is not yet visited. Therefore, New Delhi can be added at the end of the queue. And after adding New Delhi at the end of the queue, immediately visit of New Delhi becomes 1. That's all for Kolkata. Now again come back. Is the queue empty? No, the queue is not empty. Remove the front element of the queue. What is the front element of the queue? Patna. So remove Patna, add it to BFS. What are the nodes adjacent to Patna? New Delhi. Can we add New Delhi to the end of the queue? No, because visit of New Delhi is already 1. That's all for Patna. Again go back to the queue. Is the queue empty? No. Remove the front element of the queue. What is the front element of the queue? Jaipur. So remove Jaipur, add it to BFS. Any nodes adjacent to Jaipur? Yes, New Delhi. But can we add New Delhi to the end of the queue? No, because visit of New Delhi is already 1. That's all for Jaipur. Now again go back. Is the queue empty? No, the queue is not empty. Remove the front element of the queue. What is the front element of the queue? New Delhi. Remove New Delhi, add it to BFS. Yes. Now any adjacent nodes for New Delhi? No, there are no adjacent nodes for New Delhi. That's all. And again come back to the queue. Now is the queue empty? Yes, the queue is empty. Now the queue has become empty. This is our BFS. You can just see after queue becomes empty, we have got the BFS. So we started from Bangalore, then we went to Chennai, Hyderabad, Thiruvananthapuram, Mumbai, breadth-wise. Then Bhubaneswar, Bhopal, Raipur, Gandhinagar breadthwise, then Kolkata, Patna, Jaipur breadthwise, and at last New Delhi. I think with this example you can understand from Bangalore how we traverse this graph using breadth first search. It is quite simple, quite straightforward. Now let us write a simple algorithm for the operation of iterative breadth first search. Let us consider a small graph. This is our graph and the graph is having 10 vertices. Yes, 10 vertices are there in the graph. Therefore, n is equal to 10. 10 vertices are there in the graph. Let us assume the source vertex is 1. Yes, and also in our operation we have seen the visit for all the vertex should be initialized to 0. So visit for all the vertices from 1 to 10 should be equal to 0. Very good. And also we should initialize a queue. Yes, this is our queue and this is our BFS traversal. Now what we did in the operation, the source vertex was inserted into the queue. What is the source vertex here? 1. So 1 is inserted into the queue. Yes, we'll write the same in the algorithm. Steps. Initialize queue to be a queue with only v in it. Yes. Right now v is equal to 1. Initialize queue to be a queue with only v in it. Yes, we did that. Whenever a vertex is added into the queue, immediately visit for that vertex should become equal to 1. Therefore, visit of 1 is equal to 1. We'll write the English here. What is the English? Mark vertex v as visited. Yes. In general, mark vertex v as source vertex as visited. Very good. Next, what we have to do? We have to check whether q is empty or not. Therefore, while q is not empty, we have to do the while loop. We are putting a while loop. While q is not empty, yes. Remove the front element of the queue. The front element of the queue is 1. Remove it and assign it to x. Remove the front element of the queue and assign it to x. Same thing we write in English here. Remove the front element in the queue and assign it to x. And this x value should go to BFS array also. 1 will go to BFS. That statement also we will write down here. Add x to the BFS array. Yes, whatever x was 1, we add it to BFS. Therefore, x is added to BFS. Very good. Now, all the vertices that are adjacent to 1 should be added to the queue if they are not visited. I is equal to, see, we have to find out the adjacent node from 1 which is not visited. So from 1, 2 is there, 2 is not visited, therefore 2 can be considered. So for all the vertices from 1 to n, yes, 2 can be considered. Why 2 can be considered? Because there is a vertex from 1 to 2 and visit of 2 also is equal to 0. So how to write down in the algorithm? If there is a edge from x to I and vertex I is not visited, what we have to do? Add 2 to the queue. So you can just see, add vertex I at the end of the queue. And after adding 2 to the queue, make visit of 2 is equal to 1. Yes. Therefore here mark vertex I as visited. So whatever operation we are doing, exactly like that in English we are writing, that's all the algorithm. Always I say operation is more important than algorithm. When you know the operation, algorithm naturally follows. Very good. Then after 2, 3 is the next vertex. 3, is it visited? No, 3 is not visited. Therefore 3 also can be considered. 3 is added at the end and visit of 3 becomes 1. Next 4 is also there, adjacent node for 1. 4, is it visited? No. Therefore 4 also can be added at the end and visit of 4 becomes 1. Anything else? No. That's all. That's all. Again, we come back. Check whether the queue is empty. No, the queue is not empty. Therefore, remove the front element of queue and assign it to x. Remove 2 and assign it to x. So x will become 2 and 2 should be added to BFS also. Very good. Now, what are the nodes that are adjacent to 2? 5 is there. 2 to 5. But visit of 5, is it equal to 0? Yes. Therefore, 5 can be added at the end of the queue. Yes, 5 can be added at the end of the queue and visit of 5 becomes equal to 1. That's all for 2. Now, again come back. Queue, is it empty? No, the queue is not empty. Therefore, remove the front element 3 and assign it to x. Yes. And 3 is added to BFS also. Very good. Now, what are the nodes adjacent to 3? Only 5. There is only one vertex adjacent to 3, 5. But visit of 5, is it 0? No. Visit of 5 is already 1. 5 is already visited. Therefore 3, we cannot do anything. That's all for 3. Again go back. Is the queue empty? No, the queue is not empty. Therefore remove the front element, assign it to x. 4 is removed and x is equal to 4 and 4 is added to Bfs also. Now what are the nodes adjacent to 4? You have 3, 6 and 7. First let us consider 3. Visit of 3? Yes, visit of 3 is already 1. Therefore 3 we cannot do anything. 4 to 6? Visit of 6 is equal to 0. Therefore 6 can be considered. 6 can be added to the end of the queue. Since 6 is added, visit of 6 becomes equal to 1. Next, 4 to 7. Yes, 7 also can be considered because visit of 7 is equal to 0. Therefore 7 is added at the end. After adding, visit of 7 becomes equal to 1. That's all for 4. Again, check whether queue is empty. No, the queue is not empty. Remove the front element of the queue, that is 5, and assign it to x. Yes, x becomes 5 and 5 is added to Bfs also. Now again find out the nodes adjacent to 5. What are the nodes adjacent to 5? 8. 8, is it visited? No, because visit of 8 is equal to 0. Therefore we can consider 8. We can add it at the end, and after adding, visit of 8 becomes 1. That's all for 5. Again come back. Q, is it empty? No, the Q is not empty. Therefore remove the front element of Q and assign it to x. Therefore x will become 6. 6 is added to Bfs also. What are the nodes adjacent to 6? 3 and 8. But 3 is also visited because visit of 3 is already 1. 8 is also visited because visit of 8 is already 1. Therefore for 6 we cannot do anything. Very unfortunate for 6. 2 vertices were adjacent but both of them are visited. We can't do anything. That's all. Again come back. Q, is it empty? No, the Q is not empty. What is the front element of the Q? 7. Assign it to x. Yes. And add 7 to the end of the Q. Next, what are the nodes adjacent to 7? 8 and 9. But 8 can we consider? No, because visit of 8 is already 1. 9? Yes, because visit of 9 is equal to 0. 9, we add 9 at the end and visit of 9 becomes equal to 1. That's all for 7. And again check whether the queue is empty. No, the queue is not empty. Remove the front element 8 and assign it to x. So x is equal to 8 and 8 added to Bfs. What are the nodes adjacent to 8? There are no nodes adjacent to 8. Therefore we cannot do anything. Again come back. Is the queue empty? No, the queue is not empty. Remove the front element of the queue 9 and assign it to x. Therefore x becomes 9. 9 is added at the end of the queue. Yes. What are the nodes adjacent to 9? There are no nodes adjacent to 9. Therefore we cannot do anything for 9. Again come back. Is the queue empty? Yes. Now the queue has become empty. So when the queue has become empty, this is our Bfs. So you can just see in the graph, we started from 1 and we traversed the graph breadthwise. From 1, 2, 3, 4 breadthwise, and again 5, 6, 7 breadthwise, and again 8, 9 breadthwise. 10 is not reachable. So visit of 10 remains 0 at the end also because 10 is not reachable from 1. So the Bfs traversal is 1, 2, 3, 4, 5, 6, 7, 8, 9. And this is a simple algorithm. See, the algorithm for breadth first search iterative is a very simple algorithm. First, you should understand the operation. Exactly like the operation, the algorithm will come. I think it is quite simple. Now let us write the algorithm for iterative breadth first search formally. So algorithm Bfs, V is the source vertex. Initialize Q to be a queue with only V in it. Just now we did that. And mark V as visited. While Q is not empty, remove the front element of Q and assign it to X. And add X to the Bfs array. Just now we did all these operations. And again, I is equal to 1 to n2. If there is a edge from X to I and vertex I is not visited, meaning it is an adjacent vertex which is not visited, add vertex I at the end of the queue and mark vertex I as visited. That's all. Go on continuing this while loop. At the end, display the Bfs traversal in the Bfs array. Display all the vertices reachable from V. That's all the algorithm for Bfs. Very simple, very straightforward algorithm. Now let us see the program for breadth first search, C program. So now we declare Q and graph is represented in the adjacency matrix. Therefore we have an adjacency matrix ADJ 2020 and Q is Q20, that is the Q. Now We have visit also, we have BFS also, and this is the front and rear for our queue. Yes, enter the number of vertices, n. We read the adjacency matrix. Yes, the graph is read in the form of adjacency matrix. We take the source vertex also, V is the source vertex. And initially, we have to make visit for all the vertices equal to 0. This loop will make visit of all the vertices equal to 0. Then, we have to insert the source vertex into the queue. Therefore, first we increment rear and then q of rear is equal to V. Yes. Now, again, the source vertex visit should be equal to 1 that we make. While front is less than or equal to rear, this is q is not empty. This condition, while loop, q is not empty. In code, we write out front is less than or equal to rear. Then, remove the front element from the queue. Yes. Add it to BFS. Yes. And then, for all the nodes that are adjacent, add them to the end of the queue and visit for that particular adjacent vertex should become equal to 1. That's all the while loop, and that's all the thing. Then the BFS traversal is display whatever is there in the BFS, that is the BFS traversal. Then, if visit is equal to 1, it means it is reachable, otherwise the node is not reachable. That also you display. That's all the program in C. Very simple, very straightforward. Simple algorithm for BFS iteratively. Now let us understand the time complexity of BFS iterative. So let us write the algorithm here. Same algorithm. You can just observe this while loop will be executed maximum n number of times. While q is not empty, that while loop is executed maximum n number of times, and inside that while loop, this for loop will be executed n number of times. Outside while loop is executed maximum n number of times. Inside this for loop is executed n number of times. Therefore, time complexity is given by, yes, 1 to n outer loop and again 1 to n inner loop for loop. So we know the formula for this. So this is n minus 1 plus 1. Yes, it is expanded. Minus 1 plus 1 cancels. So it is equal to n. You take n outside. So n into this. And again, n into, again you expand. N minus 1 plus 1. Yes. This is equal to n into n. This is equal to n squared. Therefore, time complexity is big O of n squared. If V is the number of vertices, the time complexity is given by big O of V square. That's all. Very simple. The time complexity of breadth first search iterative when the graph is represented by adjacency matrix is big O of V square. I think this is simple and straightforward. Time complexity is also very simple, very easy. I think breadth first search iterative, you should know the operation, you should know the algorithm, you should know the C code also, and you should also know the time complexity as we have done just now. Very simple, very easy. Now let us see the operation and algorithm for breadth first search using recursion. We'll consider the same graph. Yes, this is our graph. The graph consists of 10 vertices. Yes, n is equal to 10 and the source vertex is 1. Here, this is our Q and this is our BFS. Here, visit of the source vertex is initialized to 1, whereas visit for all the other vertices is 0. This difference you should observe. Visit of the source vertex is initialized to 1, whereas visit for all the other vertices is 0, and the source vertex is also added to BFS. Now we call this function Bfs recursive. This is recursive, therefore it is Bfs recursive for the source vertex of 1. What we do here is find out all the vertices that are adjacent to 1, which are not visited. So I is equal to 1 to n, fine. I is equal to 2. Why did we consider 2? Because there was a vertex from 1 to 2 and visit of 2 is equal to 0. That we will write down in English, same thing. If there is an edge from V to I and vertex I is not visited, what we have to do? Add 2 to the Q and make visit of 2 is equal to 1. Yes, 2 is added. Yes, we will write down the English. Add vertex I to the Q and again visit of 2 is equal to 1. Mark vertex I as visited. That's all. Next 3. Because Visit of 3 is equal to 0, therefore 3. Add 3 at the end, visit of 3 is equal to 1. Next 4. 4 is added to the end and visit of 4 is equal to 1. That's all for BFS REC. Now we check whether the queue is empty. Carefully understand, if queue is not empty, remove the front element 2 and assign it to X. So remove 2 and assign it to X. We'll write down English here also. Remove the front element of the queue and assign it to X. And 2 is added to BFS. We write the English, add X to the BFS array. Now carefully understand, recursively we call the same function for 2. That is BFS of REC 2. That is here in this particular case called BFS REC of X, because there in general we have taken X. Yes. Now BFS REC of 2, find out all the vertices that are adjacent to 2. So the vertex that is adjacent to 2 is 5. 5, is it visited? No. Therefore 5 is added at the end of the queue and visit of 5 is equal to 1. That's all. Now again check if the queue is empty, queue is not empty. Therefore remove the front element of the queue and add it to X, assign it to X. Therefore 3 is removed and X is equal to 3. Now 3 is added to BFS, call BFS REC of 3. Yes, recursively it is called. Again find out all the vertices that are adjacent to 3. So what are the adjacent vertices of 3? 5. But visit of 5 is already 1, therefore nothing can be done for 3. So that's all. Check whether the queue is empty. No, the queue is not empty. Therefore, remove the front element of the queue and assign it to X. So 4 is removed and X becomes 4. 4 is added to BFS. Now call BFS REC of 4. Very good. Again, what are the nodes adjacent to 4? 3, 6 and 7. 3, visit of 3 is already 1. Therefore, nothing can be done. 4 to 6. Yes, visit of 6 is equal to 0. Therefore, 6 can be added at the end of the queue and visit of 6 becomes 1. 7, yes, visit of 7 is equal to 0. Therefore, 7 can be added to the end of the queue and visit of 7 becomes 1. That's all for 4. Now again check whether the queue is empty. Yes, queue is not empty. Therefore, they will remove the front element of the queue 5 and assign it to X. Yes, and X is added to BFS. That is 5 is added to BFS. Now call again BFS REC of 5. Yes, very good. Again find out the vertices that are adjacent to 5. 8. 8, visit of 8 is equal to 0. Therefore, 8 can be added at the end of the queue and visit of 8 becomes 1. That's all. Now, check whether the queue is empty. No, the queue is not empty. Therefore, remove the front element 6 and assign it to X. Add the 6 to the end of the BFS also. Now, again call BFS REC of 6. Now, find out what are the vertices that are adjacent to 6. 3 and 8. But visit of 3 is 1 and visit of 8 is also 1. Unfortunately, 2 vertices are adjacent to 6. Both are already visited. Therefore, nothing can be done for 6. Yes. Now again check whether the queue is empty. Queue is not empty. Remove the front element 7 and assign it to 6. Assign it to X. And 7 is added to BFS. Yes, 7 is added to BFS. Now again call BFS REC of 7. Yes, BFS REC of 7. What are the nodes adjacent to 7? 8 and 9. 8, visit of 8 is already 1, therefore nothing can be done. 9, yes, visit of 9 is equal to 0, therefore 9 can be added at the end of the queue and visit of 9 becomes 1. That's all for 7. Again check whether the queue is empty. Queue is not empty, therefore remove the front element 8 and assign it to X. Therefore X becomes 8. 8 is added to BFS also. Now call BFS REC of 8. Again, find out what are the vertices that are adjacent to 8. No vertex is adjacent to 8, therefore dash. Check whether the queue is empty. The queue is not empty. Remove the front element of the queue 9 and assign it to X. So X becomes 9 and 9 is added to the end of the BFS also. And now BFS REC of 9 recursively. Again, find out the vertices that are adjacent to 9. No vertices are adjacent to 9. That's all. Now check whether the queue is empty. Yes, now queue has become empty. So when queue has become empty, there is no recursive call. Queue is empty, there is no recursive call, and this is our BFS. You can just see the same BFS that we got in iterative, the same BFS we have got. So you can just see starting from 1, breadthwise we travel. 2, 3, 4, afterwards again breadthwise 5, 6, 7, again breadthwise 8, 9, 10 is not reachable. Okay, this is the BFS using recursive. See, if you understand iterative algorithm, recursive algorithm is also very similar. I think you can feel that quite easy, quite simple. Let us consider the formal algorithm for breadth first search using recursion. Just now we did the operation and the algorithm also. B is the source vertex. First we find out all the adjacency nodes. Yes. If it is adjacent, add it to the queue. Mark vertex I as visited. Yes. Now we check whether queue is not empty. Remove the front element. Assign it to X. X is added to BFS. Now we call the same BFS REC function for X. That's all the algorithm for breadth first search using recursion. Just now we did that, the same algorithm. The C code for BFS recursion is as follows. So front is equal to 0, rear is equal to 1, the queue, visit, adjacency matrix, ADJ, queue, BFS. All these are initialized. So BFS REC, V is the source vertex. So we find all the adjacency vertices. If they are not visited, we add it to the queue and we make visit of that particular vertex equal to 1. Now we check whether queue is empty. Queue is not empty, remove the front element, add it to BFS and call the same function recursively. This is where recursion happens. That's all. The recursive function for BFS REC. Main program, number of vertices we read, adjacency matrix. Yes, we read the adjacency matrix. Source vertex is V. And initially visit, you can just observe 1 to n, visit is equal to 0 and rear plus n, q of rear is equal to v. Visit of v is equal to 1. Just now I said for the initial vertex, visit of the initial vertex is equal to 1. We are doing that. And again we are calling BFS REC recursively. After that the BFS traversal is, you print the BFS array and then if visit is 1, node is reachable, otherwise node is not reachable. That's all the main program. I think the C function recursive for BFS is also very simple, straightforward. Now let us consider the time complexity of BFS using recursion. So let us see the algorithm here. Yes, you can just see the for loop is executed n number of times. Okay, the for loop is executed a number of times. Again, function BFS REC is called recursively. See, inside the function BFS REC, for loop is executed a number of times. Again, BFS REC is called recursively. Therefore, the time complexity is given by n plus again t of n. N plus t of n. But this will happen for a maximum of n times. Okay, it can happen maximum of n times because n number of vertices are there. Therefore, the time complexity is given by n number of times. So, this is nothing but n squared. Yes. Therefore, time complexity is big O of n squared. If v is the number of vertices, we have big O of v squared. That's all the time complexity of breadth first search using recursion when the graph is represented by adjacency matrix. I think recursion BF is also quite simple, quite straightforward.